Hey, Principles of Engineering students. A few things that we've already covered. We've talked about truss calculations, we've talked some about material sciences, we've alluded to talking about stress and strain and how the materials can behave a little bit differently. And all of that, the idea is we're building into the idea of building bridges and designing them. And while the intention was to be able to use the workshop before the spring break and coronavirus went ahead and kind of made that a little bit more difficult, what we are going to do is we're going to use some simulation software to allow us to go ahead and design and engineer and compete a little to see who can design the best bridges. So the software we're going to be using is Bridge Designer 2016, and for those of you that don't have it already installed, the place where you want to go to get it is bridgedesigner.org, and under their downloads page you've got options for Mac and Windows. You don't necessarily have options for Chromebook or mobile devices, although they keep trying to find some developers to help them expand the program, because this used to be the West Point Bridge Designer. West Point, of course, is the academy, a military academy, the first one that was actually into offering engineering programs in the United States. So one of the nice things about this is it is set up that we can run kind of a competition. We can see who's going to design the best bridges. And it used to be one where you could get some scholarship money. Unfortunately, since West Point stopped funding it, the scholarship money has kind of dried up. So let's talk about what we need to do within the software itself. So when you actually open it up, they'll always have some tips. I definitely recommend that you kind of browse through those and get an idea of what you could do to go ahead and help you out. But once you've done that, ultimately what we're going to do is we will each start our own designs. And basically after you set up the one design, I recommend that you kind of keep it as the only file that you're going to use, because part of what the software will do it will actually track the number of iterations, different versions that you come through. So in terms of setting up a bridge, what we're going to do is we'll hit OK, and then of course you could load your own file if you need to, or when you're coming back to it. But pay attention to the design requirements. There are a variety of them, and ultimately the goal is to keep the cost as low as possible. And in terms of setting it up, we actually will have a code, at least for those doing this in April of 2020. It's going to be Southeast Raleigh Magnet, and the code will be 02B. Okay, so SRM02B. And that will go ahead and make sure that we're all kind of starting at the same point. The same site cost, the elevation, how long the bridge basically needs to be, the type of load that it'll carry. And it's there to go ahead and help us kind of get started. So after you have the terrain set up, you can choose to use a template. You can do some research, look at what a Howe bridge design is, what a Pratt design is, what a Warren looks like, and you can make a decision if it's going to be one where the truss is on top or if it's going to be one where the truss is on the bottom. Certainly have some options there, or of course choose none and design it freely by hand or with some research that you've done. And just to give you an idea of how it works, what you need to do in the software, I'm going to go ahead and use the Warren truss design. And I do recommend that you go ahead and put a name into this. So design myself, and this is mostly to make sure that when I'm receiving the contest entries to see who has the lowest cost bridge, I'll be able to go ahead and identify that because that'll be part of the document. So pay attention to tips, advice that it gives you. It'll definitely help you out. To get started on this, I'm going to go ahead and start by using some of the tools within the design features. So we have joint tools, member tools, and if you're remembering some of our calculations about static determinability, number of joints and members actually matters. So I'll start by putting in the joints according to the template. You don't need to worry about the ones down below on the deck. You'll notice that a couple of those you can't actually select. But as we start placing our members, we need to remember that we click and drag. It's not just click and place. But one of the nice things about how we actually set this up is when you have a straight line, you can actually click and drag across all of them and be able to go ahead and make all of those members connected. So still creating individual ones, but good way to go ahead and see what you have. Now you can change the location of the joints as needed. You can select a member individually, and you'll actually see that in your member list, which will become important as we actually start going through the testing process. And we can choose to erase different members or joints. So we'll reestablish that one. So the other thing is, once you have all of these members made, we can go ahead and change the material that's used. So we have carbon steel, high strength steel, and quenched and tempered steel. We can change the style of it, so it can be a solid bar, or we could have it as a hollow tube. Hollow tube basically just creates the thickness of the walls rather than how much space it actually takes up. So I'm going to leave it as solid bars. We can also change the size of them. So I'm going to scale this up a bit to go ahead and make sure that it's going to work under the test, but we can use some of the different icons to go ahead and control how much we actually see. With the bridge basically set up, we now have a opportunity to go ahead and do a test command. So we can run the test load. In this case, you'll notice some colors. The colors are going to be indicating where the stress and strain are actually occurring. Okay, so we've got some compression, we've got some expansions, but when we go back to our design menu, we actually see that all of our compression and tension values have become numeric. We actually see what they're actually doing. Now I'm going to go ahead and select one towards the center here, and I'm actually going to decrease the size of that, and could change the member, could change the value, but when we actually run the test again, in this case we actually see how that fails. And failing can be a little on the dramatic side, but under status it will always show you that it failed. It can show you that the previous version actually worked. It can show you some cases of where the testing was just under process. Now, to give you some better advice about what you're doing, you can always go back and select which iteration you're at. But one of the things that you may pay attention to, especially when you're trying to get your costs down, is under Canvas, we actually had this activity 2.4.1. And what I recommend is spend some time and actually do some research in terms of what affects the cost of those members and which members are going to be stronger under compression versus stronger under tension. What values do they become more economical to use a hollow tube versus the solid bar? So the assignment actually gives a lot of the calculation information, it breaks down the costs, it gives you a lot of the same stuff that you've now seen in this video. But doing this research is going to help you enable a better attempt at bringing the costs down. For my design, every year when I pull this up, I go ahead and I give it another shot. And while this is a functional bridge for about $500,000, I've been able to get it under $300,000 fairly easily, and sometimes as low as about $250,000. Of course, I've had students try and go for the extreme other side, where they raise the cost up as much as possible. In this case, if we go up to these massive beams, we can actually see that that's already better part of $3 million. So think about your priorities, what you want to do. When you are doing this well, you're probably going to get past 100 iterations, 100 different variations. And sometimes it's going to be changing lots of things. Other times you're going to be getting down to individual members and deciding, how can I make it just strong enough, or can I tweak it just a small amount. And sometimes those differences are only going to be a couple of $100, but when you consider the number of members involved in this and the number of joints involved in this, you might start taking care about bringing those costs down by $100 or so. So I'm looking forward to seeing your entries. Again, in the description, it'll have the code that we're using as our design template. But yeah, I'm looking forward to seeing if any of you can get under $250,000, since that's definitely where I've been able to get some of my costs down to. So good luck, and if you have questions, of course, feel free to ask.